All right. So welcome, everybody. I'm super happy to be here with you, even if only virtually. So yeah, I'm Guillaume Laforge. I'm a developer advocate for Google Cloud. So that's why I'm going to show you how to deploy Micronaut stuff on Google Cloud. And I'm also, I'm the co-founder of the Apache Groovy programming language project. I'm also a Java champion, but I'm also a member of the Micronaut technical advisory board. So that's why I'm fan of Micronaut, this pretty new, pretty recent framework for creating all kinds of applications. So there will be 3 chapters in this presentation. First of all, an overview of what Micronaut is, where it came from, etc. Then I'm going to have a second chapter where I introduce you to the concept of serverless, and I tell you a few words about the platform on which I'm going to deploy those functions, apps, containers, etc. And the third chapter will be some demos to show that concretely so that you can see what it looks like. So let's start with chapter 1. So Micronaut. So Micronaut is a new, fairly recent, let's say it's not very old, framework for microservices and serverless, but not only, you can build all sorts of things, even command line applications, but yeah, there's a big focus on the serverless and microservices. The big thing that's different with Micronaut from other famous and well-known frameworks is that it's taking advantage of annotation processing at compile time. So meaning that lots of the stuff that classical frameworks do often at runtime, Micronaut does that stuff at compilation time. So it can add a little bit of time during the compilation, but otherwise in terms of memory consumption, startup time, etc., it's much faster because all the heavy lifting is done at compilation time. But I'll come back to that in a moment. And Micronaut is really the result of the lessons learned building Spring and Grails frameworks, because the creator of the Micronaut framework is Guillaume Laforge, who is the creator of the Grails framework, whose latest version is also based on Spring Boot, and we were working back in the day with the Spring team. So from all these backgrounds emerged some ideas that led to the creation of Micronaut. So with Micronaut, you can build microservices, serverless applications. That's going to be the big focus for my presentation. You can also create message-driven apps, for example, using Kafka or RabbitMQ message brokers. You can even create command line tools, command line applications. You can also do Android mobile applications, or more or less everything that has got a static void main method. So it's not just for HTTP requests and such. And you can use 3 different programming languages. You can use Java, of course, but you can also use Apache Groovy or Kotlin. In terms of features, so it's the familiar annotation-driven programming model. So you're going to annotate your services, your controllers with some annotations. Okay, this is a controller with @controller. This is you want to inject something, you're going to use @inject. So it's something that is pretty familiar and pretty common in various frameworks. Under the hood, it's using the native HTTP server, non-blocking server, to serve requests fast. There's a cool feature which is declarative, reactive, compile time, HTTP clients. That's a mouthful. But what it means is that you can declare an interface for a service you want to call. And there's going to be automatic marshalling and the creation of a client class that maps, that implements the interface you created. So you have just the impression of using the remote service as a local bin, but it's all done at compilation time. So you just create the interface, and all the boilerplate code is totally transparent and invisible for you, but you can use that interface to interact with the service. There's many features, it's called features even, a bit like plugins for different useful services. So you can do various cloud native related tasks like service discovery, distributed tracing, and there's support for different cloud providers, not only GCP, but other big cloud providers. There's a great data access layer that works with different kind of databases. And the other interesting thing to mention is that since it's a framework, we're going to speak a bit about that later on as well, that starts super fast. Instead of like mocking the server when you want to do your tests, instead of mocking the server parts, etc., it's actually the real application server that is going to start, the real native-based server. So in your test, you're actually testing a real instance of your application and not just something that is mocked or something like this. There's also an integration with OpenAPI to export your web APIs, your REST APIs, so that you can more easily document them, but get consumers of your API to know better what your API provides. So there's another, it's not a feature of the framework itself, but it's part of the tooling. So there's micronaut.io/launch. I think I have it open there. So yeah, it's right in front of me, of course. I was looking at the tabs, wasn't sure if I was in the right tab. So the Micronaut Launch project, it is a web app that you can use. There's also a REST API that you can talk to. You can even do a curl with it that allows you to scaffold and prepare a project by just configuring things in this UI. So for example, and it's quite funny because Micronaut 3.1.0 was released just yesterday. And I noticed there's a little bug here, if you see it. There's twice the latest version that is available. But, well, whichever you choose, that should be the same thing. So you can choose, okay, I want to use the latest version of Micronaut. I want to use Java, Groovy, or Kotlin as my language. I can also pick up the version. So usually it's the LTS version, the long-term support version of Java, so 8, 11, or 17. You can give your application a name and a base package to use throughout your classes, your tests, etc. You can also choose the build tool you want to use. So there's integration with Gradle, with Maven. And for testing, you can use JUnit, Spock, or Cotest. Cotest is probably more for Kotlin-based Micronaut apps, but you can use Spock for Java or Groovy, not just Groovy, and JUnit either way. And a few things I'd like to highlight with this interface is, so if you click on the features button, you can select the various plugins or features that are available, and there are a bunch of features. So for example, you want to use the, I don't know, the Kubernetes integration, and perhaps you want to talk to, which one? Let's pick up some database, I don't know, let's say, MariaDB, for example, and well, choose whichever feature you want to use. For example, ASCII Doctor perhaps for documentation, and click done. And then you can see the difference between an empty Micronaut application. So you're going to see, okay, here are the changes that have been added in terms of configuration, also in terms of build, with a, just a diff with plus and minus kind of diff. You can also have a preview. So for example, you want to see, so there's the, I selected Kubernetes, so there's a Kubernetes configuration. You can see what, since I used ASCII Doctor, there's an empty, not totally empty, but there's an ASCII document so that you can bootstrap your documentation. In the sources, you're going to see, well, this is just the class, which is a launcher, etc. So you've got you can see what the structure of the template project you're generating looks like. And let's mention this last feature. When you want to generate your project, you can download a zip file containing this project, or you can use curl to fetch the zip, or you can also use, there's a command line that I didn't mention, a Micronaut command line tool that you can use to create applications, etc. So you can install that command line for building many Micronaut applications. Or the last one, but that I haven't used yet, but there's also an integration with GitHub, so you can push this template project directly to a GitHub project. So that's pretty cool to get started with Micronauts. So let's come back here and continue. Another interesting integration is with Visual Studio Code. There's a dedicated plugin or extension which adds some support for Micronaut, and there's also the integration with GraalVM. I'll speak about that later on. Because you can also create native images with GraalVM for your Micronaut applications to get smaller binaries, and binaries, not just jars, native binaries, and have less lower memory consumption and faster startup time. So there's this integration. And overall, why, or what's the problem, generally speaking, with the classical frameworks that we use? So the pro side, the nice side of those frameworks is that you're usually pretty productive with modern framework or recent frameworks. They often provide annotation-based programming models, but it usually comes at a cost, some memory consumption, which is quite significant compared to, let's say, other languages or runtimes, and a slightly slow performance in terms of startup time. And often those problems are actually coming because of reflection, of runtime bytecode generation, or also the generated proxies and dynamic class loading. All these things are usually memory hungry or take time. So it's not necessarily the fault of the frameworks themselves, right? It also comes from Java's own problems, let's say. So for example, in terms of annotation API, there are also some limitations, and also with type erasure. So one example you'll see in the Micronaut documentation sometimes is, let's say you've got an engine service that is parameterized with generics. For example, you might have a V8 engine or V6 engine, and that would be the parameterization of the class. You cannot reflectively know that your engine is a V8 or a V6, and you cannot inject with generic parameterization. So there are some limitations due to these things, type erasure, or the fact that the annotation API is not necessarily rich enough for that purpose. When you use reflection for loading stuff at runtime, the reflection is not necessarily super fast, and that's why often frameworks try to reinvent reflection in their own way. And also with reflection, you cannot just pick, let's say, just one method or just one class, etc., but it really builds a big cache of everything that could be reached through reflection. So it takes quite a bit of memory space. Also, things like class path scanning, which is great for when, for example, when you annotate a class or service and you say, okay, you annotate with @service, @controller, @something. You're going to go through class path scanning to look at all the class paths to find all the beans that are annotated with such annotations. So it's time consuming as well. And things like dynamic class loading, well, it's usually slow. So that's why Micronaut took a different approach, using annotation processing to do that at compilation time. At compilation time, you work with sources, so you've got more visibility or fineness into what's really in the code. So for example, my example with engine V6, V8, etc., it's really written in the code, so you can see, and the annotation processor can see how you want it to parameterize a particular service. And yeah, I'm going to mention GraalVM just after. What else I wanted to say there? So yeah, another thing, annotation processing is available in Java. There's also another annotation processor in Kotlin, which is specific to Kotlin. And in Groovy, it's actually not called an annotation processor, but it's AST transformations, which allows to do the same kind of things, to look into the sources that are compiled to figure out all the richness of the annotations you've put on your classes, services, etc. The other thing I like to highlight is the Micronaut and GraalVM love story, because especially since Micronaut eliminates as much as possible of reflection, runtime proxies, bytecode generation, dynamic class loading, etc. It's also much easier to actually generate GraalVM native images, because what's complicated with GraalVM and creating native images is that if you rely on reflection, etc., you've got quite a bit of work to properly configure GraalVM to, instruct GraalVM to say, okay, I'm going to need access to this class via reflection, etc. But once you've got a native image, your Micronaut application or microservice will see an increased app throughput by 20 or 30%, reduced latency as well in terms of faster startup time. And I'm going to show you that during the demo. You can go up to, let's say, 20 milliseconds of startup time instead of several hundred, or if not 1 second of startup time. And the memory consumption usually is lower as well, because you don't have all the, I mentioned things like the reflection caches, etc. And it's also great for things like cloud deployment, etc., because it's easier to package a small binary than a big project with all its dependencies. So that's about it for my general introduction to Micronaut. We'll see some concrete code in the third part, the third chapter with the demo. Now that we know what Micronaut is about, I'm going to deploy my Micronaut microservices on Google Cloud, and particularly the serverless products, because that's mainly the products I'm focusing on and that I'm a fan of. So Google Cloud Platform is, well, that's the advertisement part of the talk, is available in many regions, many zones. You've got some great undersea cables with big fiber optics, so it's a super efficient network with data centers everywhere. There's a rich set of machine learning APIs, networking tools, databases, etc. But I'm going to zoom in just on the compute side of things, and in particular the bold ones: App Engine, Cloud Run, and Cloud Functions. If you look at the compute spectrum, usually when you go with like a dedicated server, in your own data center, or your own basement, your server under your desk, you have to care about all the layers, including physical hardware. When your hard drive fails, you have to change it potentially, in the middle of the night. As you go towards the right of this screen, let's say, of this slide, you're going higher into the layers, and you have to focus more on the upper layer, and you don't have to bother too much about the layer at the bottom. So with virtualization, with VMs, you don't need to care about the physical hardware. And then you're going to move into the container space, things like Kubernetes, where you don't have to focus on the virtual hardware either, and not so much on the operating system, although, in a container, you specify the operating system with the base image that you need. And then further to the right, that's really where you enter the serverless zone. So on Google Cloud, you've got Cloud Functions, where you really focus just on bits of code at the granularity of a method or a class at most. With App Engine, it's going to be applications and modules or services of an application that you deploy. You don't need to care about what's below. and not even about the runtimes, like the language, the JDK that is used. With Cloud Run, which is a bit of a in between things like Kubernetes and App Engine, you're going to deploy serverlessly containers. So you focus on your container and what's up in there, and all these things are in the serverless zone. When I say serverless, what do I mean by serverless, and particularly the characteristics? So there's an operational model standpoint, because from this standpoint, what is serverless is stuff that is usually fully managed. You don't have to care about the infrastructure. So I mentioned the bottom layers you don't have to focus on. So you don't need to think about the servers, the hardware. Since this is an environment that is fully managed by the cloud provider, you also don't have to focus on the security, because if there are vulnerabilities that are found, it's going to be the cloud provider that's going to patch those vulnerabilities. Also, a key aspect is the pay only for usage. So you're going to pay only for the resources that you need, and not for idle capacity. So it's not because there would be a server that is waiting for requests that you're going to pay for that server. Instead, you really pay just for the duration of your requests. And the other aspect of this with infrastructure management and also stateless programming, but that's going to be my next aspect about programming model. It's also a platform that is usually scalable, automatically scalable, meaning that if you've got, I don't know, 1,000 of users, concurrent users, and then suddenly you got twice as much, 2,000 users, then you're going to pay twice as much. But perhaps your application is only used at peak times, like let's say you're generating some reports daily at midnight. Perhaps the big traffic, the peak is going to be at midnight, but past 1 a.m. there's no traffic. And for the rest of the day, you don't have to pay for capacity, because there's perhaps no instance serving your application. So there's scaling from 1 to n to accommodate for incoming traffics and increased traffic, but there's also scaling down to 0, in the sense that you don't need servers to serve your application if there are no requests. So this scalability is handled automatically by the platform. From a programming model perspective, you tend to write more service-based architectures, or also event-driven architectures, reacting to various events coming from your cloud, from your infrastructure, from your project. And the other important aspect is to program somehow more defensively in a stateless fashion, in the sense that, as I mentioned, that the scaling can be scaling to n or back down to 0. Potentially at some point, your instance serving your application may be they may be all decommissioned, and no server or instance is serving your application. So it means that if you saved something locally, for example, on the local file system, perhaps this instance is going to be shut down, and when there's a new request that comes in, a new instance will be spin up, but at that time, well, you won't get what was on the file system of the previous instance. So you have to think, when you're programming your services, etc., to think in terms of a stateless fashion, so that you can accommodate for things that would be cached that are not cached anymore. So you may load from a cache or something. So you have to think about this when you're programming your services in a serverless world. So the three products we're going to focus on are Cloud Functions, App Engine, and Cloud Run. Cloud Functions for source-based, event-driven kind of functions. App Engine for API backends, web apps, etc. And Cloud Run, anything else, I would say, that you can containerize that are receiving and responding to HTTP incoming requests would be a great fit as well for Cloud Run. So let's zoom in a little bit on Cloud Functions first. I often think of functions as a service, as a kind of a glue, a cloud glue, in the sense that it's a great fit for gluing various services together, reacting to events, and call other services or products or APIs, etc. So you can there are two flavors of events that Cloud Functions can receive. So there's HTTP events. So you can also get incoming requests from HTTP requests to your function. But there are also background events. So when I say background events, it's things coming from the cloud, like a new message on PubSub, a new file in a cloud storage bucket, things like that are events, and you can react to event and have a function being triggered when such an event occurs. In terms of use cases, well, you can integrate easily with all sorts of services, APIs, or third-party services. It's a great fit for webhooks because you can receive HTTP incoming requests for IoT backends if you want to react to perhaps sensor data, things like that. For lightweight data processing, if you want to transform some data, things like chatbots, etc. There are different runtimes that are available in different languages. We're interested in Java here, so you've got Java 11 that you can use for that. And yeah, on this one, I was mentioning some examples of events that Cloud Functions can receive. But Cloud Functions is also used for things like chatbots. For example, when you create actions on Google that are chatbot kind of conversations on things like Google Home devices and such, you can react to incoming chat messages. It's an event, basically, that you can react to and create conversations with end users. So it's a great fit for reacting to all sorts of events, for things like webhook handlers, or more generally speaking, asynchronous operations. And you don't want to think about the underlying runtime. Okay, you've got a Java 11 runtime that you can use for lightweight data transformation, for webhooks. In terms of constraints, well, you have to use the version of the language or runtimes that are available. You can't necessarily, so for example, there's not yet Java 17 runtime for Java, so you have to use Java 11 for now. You got to interact with events, yeah, and what else I could mention? Yeah, the current concurrency level. The one function can only serve one event at a time. So if there are many events at the same time, there are going to be several functions running as different instances, and there will be a cold start for each of them. So you'd see more cold starts with something like Cloud Functions, meaning that that's why it's not great for web front ends, because you don't want your end users to suffer from the cold starts. If it's a web-facing front end, you should use App Engine or Cloud Run. With App Engine, many runtimes available. Currently, Java 8 and 11, not yet 17. You can deploy many services or versions of your services, meaning that potentially you can easily do A/B testing, blue-green deployments, etc., thanks to traffic splitting to different versions of your services. You can have higher levels of concurrency, like 80 concurrent requests, custom domain names. That wasn't the case with functions. And a cool thing as well is the static asset serving for CDN. I'll show that during the demonstration, because you can make cold starts transparent for the user, which is something cool. So it's great App Engine for stateless applications, for HTTP workloads. So it's great for web frontends, backend APIs, and such. Built-in CDN, that's great. Traffic splitting for deployments, A/B testing, and so on. And one limitation that's going to be lifted with Cloud Run is you can't support things like WebSockets, HTTP2 streaming, gRPC streaming, or server sent events. So it's because HTTP requests are buffered, so you can't get a stream of events flying to and through your application. But with Cloud Run, that's not the case. With Cloud Run, instead of deploying functions or apps, you're going to deploy containers. So what's great with containers is that you can put any language, library, or binary in your container. There's a rich ecosystem of base images as well. So you get the flexibility of containers even if there's a slightly higher learning curve, potentially, you get that flexibility, whatever you want to put in a container, as long as it's serving HTTP requests, but we'll see that in a minute. And the agility or velocity of serverless, because you're going to get the automatic scaling from the platform, from a serverless platform. Cloud Run is also based on open source underpinnings. It's implementing the Knative, it's an open source project, the Knative API, which is something that, which is a layer you can install on a Kubernetes cluster. So Cloud Run containers that you've created, you can run them elsewhere, not just on Google Cloud Platform, which is great also for portability if you don't want to be, locked in a particular cloud provider. In terms of contract for your container, you should listen on 000 on dollar port. Your application shouldn't take too long to start. What else? You've got 2 vCPU by default, I think, half a gig of RAM, but you can go up to 8 or 6. You can get up to 1,000 concurrent requests per instance, as well as up to 1,000 containers. So that means that potentially you can have 1,000 containers serving 1,000 users. So that's potentially 1 million concurrent requests to your containers, which is pretty cool. So good fit, great fit for stateless workloads, for HTTP requests response kind of workloads. And it supports WebSockets, gRPC, server-sent events, and I'm going to show that in the demo. It scales pretty quickly as well. And you can put anything in your container. Containers add a certain level of complexity in the sense that you need to be at ease with containers. And something I didn't mention, but in terms of build process, you can build within the cloud. You can build also with cloud native build packs. So you can build, when I say you can build your container locally on a machine and push that into a container registry, for example, and then deploy that from the registry, or you can push your code and use Google Cloud Build to build in the cloud, or there's also the third option, which is native cloud native build packs, which take your sources and going to build in the cloud and deploy directly. There's no, unlike App Engine, there's no built-in CDN, or it's a little bit more complicated to set up, but you can use Cloud CDN and such if you really want to. But App Engine came with certain built-in batteries like Memcache, etc., which is not available in Cloud Run. Otherwise, that would be tied to the platform itself and less portable potentially. All right, so that was a quick intro to those serverless solutions on Google Cloud. Now it's time to have a look at how to create functions, apps, and containers with Micronaut, and how you would deploy that into App Engine, Cloud Functions, and Cloud Run. So let's switch to this screen. Okay. So I've got, I'm going to show you, and something I'd like to mention before showing the code. On GitHub, I have a little project in my repository. So if you go to, github.com/glaforge/mn-gcp, so Micronaut-Google Cloud Platform, basically, all my functions, App Engine apps, and containers are available there. And I just migrated them to Micronaut 3.1. Although I didn't yet deploy to Google Cloud because I hadn't finished before the beginning of the talk. But yeah, you've got the sources, and there are a few light instructions on how you would deploy things. So the first thing I want to show you, I'll start with functions. So I've got 2 functions that I have. So the first one is the pub/sub function. So I'm going to show you a pub/sub function, how you create a pub/sub function with Micronauts. So you're going to use, yeah, something I didn't mention with Cloud Functions is that each functions runtime has got what we call a functions framework. So it's a lightweight way, an API to code against when you create functions. And what's cool with that framework, it's not just a framework, but it's also an, how could I describe that? An invoker. In the name that we use is invoker to describe that, but it's the ability to run functions with that framework. So what Google Cloud Functions is using within Google Cloud to run your functions is that framework. It means that it can also use that runtime framework to also run your functions locally on your machine, or even deploy your functions elsewhere and not just on Google Cloud Platform. So you've got a certain level of portability as well with Cloud Functions. So when you create a pub/sub function, you have to implement the background function interface. So it's coming from Google Cloud Functions. So it's an open source project and a library that you can use. You can, so I parameterize this with a pub/sub message class, which is my own class to describe the kind of payloads this function is going to receive. And in that case, we're going to receive pub/sub messages, okay? So I'm not injecting, but parameterizing this function with that class. So there's automatic marshalling and marshalling from a pub/sub message in a topic. There's one thing, I'll mention that afterwards. So when you implement that interface background function, you've got to implement the accept function, which takes the parameterized type pub/sub message and a context object, which contains some metadata about the when the message arrived, etc. The other thing that I wanted to mention is you can extend this class, which is coming from the Cloud Functions integration and support from Micronaut, which is going to somehow inject the Micronaut behavior in your Cloud Function. So for example, here I'm using @inject to inject a service. So I created a simple logging service just for the sake of this example, which is going to log messages directly. So I could have just, written log info, etc. in my accept method, but I just wanted to show you how I can inject a logging service with the usual annotations you're used to. So I've already deployed that, not the right screen, I've already deployed that function. And if I, let's say, do I have it elsewhere? So if I have a topic somewhere here, I've got my events topic, and I can do, where is it? I always forget where I have to, where is it? I want to push, oh yeah, it's down below. Messages, I can publish a little message. Hello everyone from Paris. And I can publish that message, and it's going to trigger my function, and I can have a look, for example, at the logs and see whether my function. So I didn't show you how to deploy my function, but we're using the gcloud SDK command line to deploy things, but it takes a couple of minutes. So for the sake of time, I just want to quickly show you the deployed function. So yeah, there's, hello everyone from Paris, that is visible here because my function was invoked. The other kind of function that I want to show you, that's so not this one, but this one for webhooks. So this one is receiving HTTP requests. So this one, compared to pub/sub functions where you implement the underlying functions framework, background functions from the functions framework, here it's a usual Micronaut controller. So I just, you don't really know that it's actually going to be deployed as a function on Cloud Functions. So I just say, okay, I annotate this as a controller responding to webhook, and I'm producing some text plain text. When you call get on basically /webhook, I'm going to return, okay, webhook controller ready. I can also specify, okay, this is a post method, and I can output the post, the body that's been posted to my function. So here, perhaps I'm just going to I'm going to go back here into Cloud Functions and do webhook. I'm just going to use instead of doing a curl, I'm going to use the testing facility that's available there. So let's say message, hello again, and it's going to call my Micronaut app as a function, wrapped as a function. Oh yeah, it's yeah, because I can't specify the URL, so I should access it via the trigger. So that would be here, and instead of webhook, so that's the webhook function, and I listen to /webhook. That's my path. So that's indeed the message you saw in the well. So it's a simple example. But otherwise, this a Micronaut application could be deployed as a standalone app or run locally, just normally without the context of Cloud Functions surrounding it. So that's it for functions. Let's go to App Engine. For App Engine, I built another web application with my fruit controller this time. So I have an application. So if I go, where is it? Okay, I'm just hiding the floating point. Yes. So where is it? Yeah. So I have this application that I deployed, where if I go to /fruit or fruits, what did I use? No, /fruit. I can see things like fruits, apples, bananas, strawberries, etc. And I also have some static assets there, which are actually defined here. So HTML, CSS, etc. And those static assets, because I configured my App Engine Micronaut application to use the built-in CDN, those things are served by the CDN immediately, even so without having to wait for any potential cold start if there are no applications serving my, no instance serving my application. So for example, so let's reload. I don't know if I'm going to face a cold start. Yeah, no, because I accessed the underlying service. Because this is serving the static assets directly, but I'm populating the values of this drop-down by calling the backend API of my App Engine app. So I don't see a cold start because the static assets of my, PWA or rich application served directly, but potentially the backend APIs that I need are going to have a cold start, but it's not really visible for the end user. Yeah, I'd like to show you something. So I also have, where is it? No, I think I need to stay there. If I go back here, I'd like to show you. So I built also the same, an equivalent app, but with GraalVM. So this time it's not fruits, it's going to be vegetables. My vegetables, so it's pretty much the same thing basically under the hood, same kind of annotations, etc. And the thing is, so if I run my application locally, I'm going to use Gradle run. If I run my application, you're going to see, normally not through GraalVM, it's going to take, here, a bit more than 1 second. Let's rerun it and see 1 second. So usually it ranges between, in terms of startup time, between 8 800 milliseconds up to 1.2 seconds or something like this. It's not that slow, right? But what I did was I added the GraalVM integration to build, and I'm not showing the build here because when you build something with GraalVM, it takes roughly 3 minutes or so to build, even for a simple hello world kind of applications. But I built it with I must have the comment somewhere. You can build with Gradle Docker native image, but I'm going to run because I'm on a Mac. I built the native image within a container. That's why I used Docker native image, not just the native image goal. But I can run my service, my Micronaut service within Docker as a native image and look at the time it takes to start up. So 256 milliseconds. Oh, that's on the high end. And usually it's more in this ballpark, 36 milliseconds, 41 milliseconds. So it starts much, much more rapidly, sometimes up to 10 times or 20 times faster than when it's not a native image for GraalVM. So when you deploy that as well in the cloud, that's also faster to start up, and also uses it's using less memory. The last little demo I'd like to do is with Cloud Run. So with Cloud Run, so I also deployed on Cloud Run the vegetable backend service with a native image, so that works. But I'd like to show you something else, this time with Cloud Run. It's the streaming aspects. So for example, I think I'm going to show you the demo first here. That's this one. So let's reload it. I'm using server send events. So if you want to use server send events, webhooks, HTTP to streaming, gRPC streaming and such, it's not possible on Cloud Functions and App Engine, but on Cloud Run, you can use that. So here it's a simple server send event. Now I'm going to show you what it looks like in terms of code. So I'm going to, every half a second, I'm going to create and throw a dice, actually. So my dice is here. I'm creating a dice with a random number from 1 to 6. And I'm using the reactive programming interfaces using RX Java. And I'm creating a ticker. So every 500 milliseconds, I'm going to tick. And I also have another flowable object to create dice rolls. So each time this flowable is invoked, I'm going to create a new dice. And after 100 requests, I'm going to stop the flow. And then I'm going to return this zip. So for each tick, I'm going to call the create event, which is this event class is actually the server sent event support from Micronaut, and I'm going to create an event per tick. So this is going to be a dice roll, so from 1 to 6, and I'm outputting both the dice roll, the value basically, as well as the ID, which is the counter. So that's why you see here the ID of the event and the value, the marshaled value of my dice roll. So that was it. And yeah, as I mentioned in the code is available there on Laforge and GCP, and there are instructions on how you can deploy these things. So that's about it. I showed how you can deploy and write functions, apps, and containers and deploy them on Cloud Run. And I'm happy to answer any question that you may have regarding Micronaut or the serverless solutions. Thanks.